is finish up our discussion of convolution. Last time we talked about the concept behind it, what it's used for, how we compute it. Today we're going to talk about various properties of convolution, treating it as an operator and seeing which properties apply to it and how that manifests itself in a systems context. And then we're going to look at an idea that we're going to need for the future, namely zero padding, and what effects that has on convolution results. Excuse me. And after that, we're going to look at the convolution of periodic signals. And that's going to lead us to a new kind of convolution that comes up when we work with discrete time systems, and that's circular convolution. So we're going to come up with a set of tools for how we can compute this new kind of convolution. It's going to rear its ugly head when we get to doing convolution with transforms. So we're trying to lay some of that groundwork so we understand the terminology and the operations when we get there. But first, in terms of properties of convolution, when we have a new property like addition is an operation, so the subtraction, multiplication, division, those are all operations, and those operations may have certain properties. And you probably went through this in the 6th grade math, assigning these different properties and seeing how they work with these different operators, like testing whether an operation is commutative, associative, distributive, and how it works in special cases. We can address that with convolution as well. And it turns out convolution is a commutative operation. If I just wrote this up here and you knew nothing about convolution, you would look at this statement and say, oh, that's true. Interpreting this star as multiplication instead of convolution. Multiplication is an associative operation. Excuse me, it's a commutative operation. Commutative implies order doesn't matter. In our case, it means if I convolve with x with h, I get the same answer as if I can convolve h with x. Or in our implementation, it doesn't matter which of the two systems or signals we're keeping and which one we're flipping and shifting, we get the same answer. So which one we put without an index change and which one we do, we get to choose. And so while commutative as a property means the order doesn't matter, in our interpretation that means we get to choose which of the two signals we're going to flip and shift when we do the actual computation of convolution, which is good news for us because particularly if you're doing it analytically, we can always choose the simpler function as the one we're going to manipulate, move around, and redraw. So that's kind of helpful. It's also associative, and when we say associative, probably in your mind you should go to groups, and how we group things doesn't matter. Again, if this was a multiplication statement, this would be true. If I multiply two functions, take the answer, multiply by the third, I get the same answer as if I pre-multiply the second two and then multiply by the first. Well, also the same for convolution. This means if I have to convolve do a sequence of convolution operations, how I do them, what order I do the groupings in doesn't matter as well. I can choose any way that I want. I can take two signals and convolve them first, and then take that answer and convolve it with the second, or with the third, excuse me. Or we can convolve the second and third first, and take that result and convolve it with the first function, and both those sequences will give us the same result. We interpret this from our system understanding, though. It has another meaning as well. That is, convolution is what a linear time invariant system does when you put in a signal into it. It convolves that signal with its unit sample response to produce an output. And so I can interpret this left-hand side of the convolution associative property. I'm taking some input signal and running it through a system that has a unit sample response each one. And what comes out is the convolution of those. That's the output, the Y1, if you will, of my system. And if I take that result and convolve it with another unit sample response, meaning I follow it with another system that has its own unit sample response, what comes out of here is, well, convolution of this with this, and we get some answer, some output sequence. I could have achieved the exact same output result by doing things in a slightly different order. This side of the property tells me I could have first taken the two unit sample responses of my two in series systems and pre-convolved those as my first operation. And then taken that convolution result and convolved my input signal with it to get the same answer. So I could have done it either way and gotten the same output signal. This also gives me, from a system standpoint, a way to take two cascade combinations or two series combinations of two different systems with two different unit sample responses. I can treat them as one system that has an overall or an effective unit sample response that is not the sum of these two, but the convolution of them. So if I'm trying to simplify a system, if I have a cascade combination of them, I can combine series blocks this way in a block diagram. I can convolve their unit sample responses to come up with an overall unit sample response. And that's what this associative property equation tells me. Superposition. Excuse me, distributive property is just a restatement of the superposition principle. And if I wrote this equation and told you we were talking multiplication and addition, you'd say, yeah, that's right. Because as an operator, multiplication distributes over addition. Well, so does convolution. Convolution distributes over addition. And in our systems interpretation of this, we could say this is just a restatement of linearity. Because it says, if we look over this side anyway, it says if I have a system with a unit sample response H1, and I put a signal X1 into it, well, what comes out is the convolution of those two. So we come out, this X1 convolved with H is what we're calling Y1. And then if I take another different signal X2 and run it through the same system, well, that convolves it with H, and I create another output Y2, then that should be equivalent to, well, putting in those two signals, the sum of those two input signals together, then running them through the system, I'll get the same answer. And that's exactly what linearity told us. If I can break things up into simpler signals, we just simply add up the responses if we add up the inputs. So addition works the same on both sides of the system. And since the system is represented by the convolution operation, the convolution has to act that way as well. So that's the mathematical statement, and this is our system interpretation of that. Although it can also have another interpretation. This picture. We kind of exchange which ones we're talking about. Here I have a system that's created from a parallel combination of two other systems. Each has their own unique unit sample response. I'm putting the same signal into them, and I'm adding their outputs together to make my final output. So I have a parallel combination of two systems, unit sample responses H1 and H2. And this side, the right-hand side of the equation says, well, let me find the output of this first system. Well, that's just X convolved with H1. And let me find the output of the second system, that's just X convolved with H2. Add those together. According to this, I get the same answer if I take that signal X and convolve it with a combined system whose unit sample response is simply the sum of these two. And both of these would produce the same output. And so this gives us a way to come up with the effective unit sample response of parallel combinations of circuits and systems. It's just the sum of the unit sample responses. So unit sample responses convolve in series and add in parallel. And that comes directly out of these properties. Questions on that? That's our systems view of what those different properties mean for convolution. When we convolve things and then delay the signal or input signal or the unit sample response. So let's say I've got some signal x of n, the system h of n, I convolve these two signals, I figure out the output is y of n. And then I ask, what happens if I put in x of n minus a time shift or an index shift? And run that through the system. Well, we know from shift invariance that if I delay the input by n1, I better delay the output by n1. That is shift invariance. And so go back off and say, well, that means that convolution, if I delay either of the two signals, I just delay the convolution result by the same amount. It was also a shift invariant operation. Now, strangely enough, if I convolve two signals where they're both delayed, even by different amounts, the delays on the result of the convolution is accumulated. I would get the delays for each of those delaying my output or the convolution result. And so again, however a linear time invariant system operates, that's how convolution has to operate as a mathematical operation, because it's describing what happens to input signals and how the outputs are produced by linear time invariant systems. Okay. There's an important property that's going to help simplify our life quite often. That's the question of what happens if I convolve any signal with some unit sample sequence. And we have a parallel to this in continuous time systems. So if we convolve x of n with a deltas of n sequence, we get back x of n. However, if we delay that unit sample response, with x of n, you may remember what happens to your sequence. We delay the sequence by the same amount that the delta was delayed. So a way of shifting a signal is to convolve it with a delta sub n minus some time shift, sample shift. So pictorially, if we had some, let's draw a picture. We had some x of n, I don't know, versus n. Maybe it's got some values before. Let's say that's a 2, let's say that's a 1 over here, it's 1 minus 2, it's 0 back there, and I don't know, let's make it 3 here. Let's call that 1, and let's make it kind of easy to spot here. So 1, 2, and 0 after that. Just making up segments. So it's 1, 2, 3, 2, 1, little staircase up and down. And if I convolve that with a delta n minus 2, which sits over here at 2 and is 0 everywhere else, then the convolution of those two, I guess we'll come over here, picks this whole thing up, and wherever n equals 0 was, and now is now at n equals 2. So at n equals 2, I'm going to get my value of 3. 2 there, 1 there, 0. 2 here, 1 there. All zeros after that. So wherever was n, we shift that over to wherever this is. Wherever n was 0, we shift that to where the unit sample sequence was. So again, a systems implication of that. We've been using these delay blocks, z to the minus 1. In our block diagrams for difference equations, right? I put x of n in, what came out was x of n minus 1. Can you tell me what the unit sample response of this delay block has to be then? That's find h of n. This block delays my signal by 1 sample. Delta of n minus 1. N, we can involve it with a delta of n minus 1, we get x of n minus 1. So this has to be the h of n of our unit samples, of our unit delay. And if this was a 3-sample delay, we would be deltas of n minus 3. So a delay simply has a unit sample response. It's a delta function with an appropriate delay. All right, that's the properties. Questions on those? See how they fit in the system context? Okay, now we're going to spend a lot of time talking about zeros, and we're not going to understand why we're talking about zeros, what this is for. We're going to talk about an operation that does absolutely nothing to your signal. Doesn't break anything, doesn't hurt anything, makes it look a little longer, but it's okay. It's going to seem useless. We're going to need it, though, because there is a time coming up, not too far distant future, where we're going to need this operation to come and save the day. So let's lay the groundwork so we're ready to have it come and bail us out when we need it. It's an operation called zero padding. Literally means add zeros. Usually it means appending zeros to the end of a sequence. And we use it in convolutions. So we add on a bunch of zeros at the end. We could add them at the beginning. It also works there. When we talk about zero padding, we're talking about adding some extra zero sample values to a signal. So if we have a finite length signal x of n that's 0 everywhere except 1, 2, 3, 4, 5, 4, and then it goes to 0. The zero padded version of that would say, no, that's 1, 2, 3, 4, 5, 4, 0, 0, 0. Now, if this was truly, these were the only non-zero values, this is equivalent. I'm just explicitly telling you, well, I've got some zeros there. So I'm really not changing anything, I'm just telling you about it. Okay. So it makes the sequence appear longer, but it doesn't change its non-zero length. Remember, that's what we were looking at when we were predicting convolution start indexes and end indexes and convolution lengths. We were looking at non-zero lengths, non-zero steps. Question?
Is there a reason that you intended 4 zeros, or is
just an arbitrary number. Yeah. 4 is not a magic number. It could be any. Now, when we get to needing it, there will be a magic number that we are going to want to use. But for now, zero padding is an operation. It can be any number appended. Usually at the end, could be at the beginning. So that's what this says. We can append those zeros to the end or the beginning, typically the end. And now we would ask, does that really affect anything? Does that affect the convolution that we're used to? The short answer is no. And we can prove it pretty easily. Right? Here's a finite length sequence, 1, 2, 3, 4, and then presumably 0 everywhere else. And we can involve that with the finite impulse response, 5, 6, 7, and we can use non-causal ones, doesn't matter. We plug it into our sum by column table methods, and we use all of our knowledge about start indices and lengths, and we get an answer. And my spreadsheet is right, we've got a good answer. If I do that again, and I put a 0 in front of my x, and a 0 after it, and a 0 in front of my h, and 2 zeros after, and run these signals through a convolution, including the zeros, so I put enough columns and rows to accommodate that. So you get the extra zeros in my h showing up here, the extra zeros in the x showing up here. Run it all through, and you get the exact same answer. At least all the numeric values of the convolution result aren't changed. All I get is a longer answer with some more zeros
on either side of it. So I don't affect the numeric results. I do affect the number of answers I get. I can still use my same formulas for telling me, well, how long is the convolution result going to be? Well, it's going to be longer if I count those zeros. If I count the non-zero lengths, I'll still get the correct number of non-zero samples. And if I count these as starting indices, I'll get the correct starting index for my longer version. If I start counting only the non-zero values, I can get the correct starting index for those as well. So as long as you're consistent, as long as you stick with how you're treating and talking about your signals, the answers will come out fine. And so when we do convolutions, we don't have to worry about it altering the length of the result. If you count those zeros, particularly leading zeros, in your starting index, it will change the value of the starting index, but it won't give you the wrong answer for where your non-zero samples start. And it won't affect convolution values. Right? So that's what we saw in this result. If you did it without zero padding, you got the same answer as you did with zero padding, just things were shifted over a bit, but all the rest of the indices and the answers lined up fine. The starting index of our first sample out of the table was different, but our starting index for the non-zero samples was the same as was the ending index. So again, if you're consistent, you get the right answers. And if you notice, the convolution result was zero padded as well. You put an extra zero in front and behind the x. You put 1 0 in front and 2 zeros behind the h, and what came out? The non-zero values of y came out with each of these 2 zeros on its result, and all 3 of the appended zeros showed up at the end. So we just kind of tag them on to the answer. Any ones at the end, front and back. Okay. So moral of the story is, if we particularly are starting with a finite length sequence, adding zeros is fine. In fact, it's correct because those samples that you're adding really are zeros. You're just now accounting for them, you're representing them. It won't affect the results of the convolution as long as you do your bookkeeping right. So it should be a very benign thing to do. Also seems like a waste of time because you could have gotten things with a much more compact table. Well, where it's going to come into play is when we start playing with this game, doing convolutions of periodic signals. If either x or h is a periodic signal, maybe the most straightforward one is, think about some system, a linear time invariant system, and I put in a sine or cosine signal that somebody turned on a long time ago, and we're leaving it on. So I have this forever cosine, discrete cosine, so the sample value is a repeating pattern of cosine with a certain period. When I put that into my system, forget about discrete time, just think about linear systems. If I put a cosine, back in 228, if I put a 10 hertz cosine into a linear time invariant system, what had to come out? 10 hertz cosine. Cosines and sines and complex exponentials are what we call eigensignals for linear time invariant systems, which meant LTI systems are not allowed to change their shape, not allowed to change their frequencies, just periodic. So same thing for discrete time systems. If I put in a periodic discrete time signal with some period n, what comes out has to also be periodic in n. If it's linear, that's got to be true. Since convolution is the operation that describes a linear time invariant system, convolution as an operation on a periodic signal also has to produce a periodic signal with the same period. So it's got to behave just like linear time invariant systems do. So if I put a cosine, a discrete cosine, into a convolution operation, I better get some form of the same cosine. Maybe it's bigger or smaller, maybe it's got a different phase term, but It's got the same basic frequency, better be there. So let's do that. Here's a signal that has a period of 4, a discrete signal. It goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And just keeps repeating. And we assume that was been doing that a long time before. It's still going to do it for a long time after. And we're going to run that through a finite impulse response system that happens to have this kind of finite impulse response. Here's my H of n. Notice it's like completely non-causal. Got to be stable because it's FIR. But it's only got 3 samples in the unit sample sequence. N minus 2 has a value of 5, and minus 1 has a value of 6, and the 0 is 7. Mechanics of convolution, we can predict what's going to come out. So you do it by your flip and shift or your table form, run through, and you find you get this as an answer. And notice we still have a pattern that repeats every 4 samples. So we changed the shape a bit, but it still has the same periodicity. You have a period of 4 went in, period of 4 came out. And, okay, let's play fair. I'll use a causal H of n. That's even longer. It has a length of 4 now. So I have a periodic signal with length of 4 and a non-periodic one I'm convolving it with. And if you do that convolution, well, we get some lead in, but then we get a period of 4 repeating pattern. So if I convolve a periodic signal with finite unit sample response, we're still getting back the same periodic signal like we're supposed to. And if I have a period of 5 signal, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, involved with that same unit sample response, or the first one we tried with length of 3, we still get a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 period discrete time answer output from convolution. So far we're obeying all the rules. We can use periodic signals and non-periodic signals. What happens if I convolve 2 periodic signals? The systems thinking, what would that be? That would be like putting a cosine into a system whose unit sample response is also a cosine. And we're saying that periodic can have the same period. So I'm putting a cosine signal into a system whose natural response is the same cosine. That's an oscillator. Right? Something that has a unit natural response, it's a cosine without dying out, that would be an oscillator. And I'm hitting it with the same frequency I want it to go at. No surprise, the output's going to have be periodic, be a cosine at that same period. As long as these two started off at the same period. However, to get that result with convolution, we have to be careful. We've got to have to use a computation method called circular convolution. Here's the kind of picture we're used to with convolution. It's most easily seen with finite length sequences. I have an X of n, I've got an H n, I've got to flip and shift over these, and at each position that I shift it over, I'm going to multiply stuff and add them up. If I make one of these periodic, well, all right, I got one that's periodic, another one that's finite. I can still choose one to flip and shift and move it by. If I'm got 2 periodic signals, though, when I'm flipping and shifting, I've got stuff falling off the end, stuff coming back around. I've got this repeating pattern of stuff happening. And so we have to compute that in a different kind of way than we do our linear convolution, particularly when we're doing analytical kind of results. And so to do this, we need some help. We need some new tools. And the easiest tool to do this pictorially is a circular diagram that we introduced way back in the beginning for periodic signals. I only talked about them briefly because we were only going to need them for this one particular context, circular convolution. But if I had two periodic signals, x of n that has 4 samples and it repeats, 1, 0, minus 1, 2, 1, 0, minus 1, 2, and so on. Now we can involve it with another 4 sample period signal. This h is 1, 2, 3, 1, 1, 2, 3, 1. Both of these have a period of 4. I have a shorthand way to draw those, to depict those, that repeating pattern, using a circle. And I can use those circle diagrams to compute the circular convolution result. Looks like this. Here's how I display x of n. It has 4 samples in a period, so I draw a circle, start here at the 0-degree line here, and break up the circle into however many segments I have, different samples. So I have 4 samples, I need 4 segments. And then I start over here, and I put in here the n equals 0 value for x. And I go work back counterclockwise. N equals 1, n equals 2, n equals 3, and then it's repeating. Right? And I can actually put the values in. N equals 0 is 1, then 0, then minus 1, and 2. So this would be our shorthand circular diagram for this periodic signal x. And likewise, I could create one for h. Start over here, put h of 0, h of 1, h of 2, h of 3. So h of 0 looks like a 1, h of 2 is 2, and 3, then 1. And I have a pictorial display of this periodic repeating signal. And I just keep going around and around and around to create each period of that signal. How do we use this for convolution? What we're going to do, remember convolution, we got to take one of the signals, we have to flip it, and then for each value of n on the output, we're going to shift it one position. So I need a way to look at one signal relative to the other. So we'll choose one of our signals, and for example, this one, h, we'll say, okay, this h of n now is h of k. I don't have to change anything there. Just change the variable. And x of n minus k, n k is our independent variable. So if this is x of k, then x of minus k is that reversed. So starting here at 1, instead of coming around this way, we'll go around clockwise. So x of minus k has x of 0 here, x of 1, x of 2, x of 3 here, and goes backwards. And then when I want to shift this for each value of n, I'm going to rotate my x relative to the h. Everybody okay with how we forward and backward? So if counterclockwise is our normal direction, when we do the minus k, we go clockwise, still starting at the same point. When to do a convolution, we're going to want to look at this signal relative to this signal as we change the rotation of x relative to h. So we'll make this inner-outer diagram. We'll put our h on the outside, we'll put our x on the inside with the appropriate rotation. So for example, to find y of n equals 0, we'll put our h around here, that's h of k, x of 0 minus k. So there's no rotation in that one. So we'll do our h's. Our 1, 2, 3, 1 pattern, our x of minus k pattern without any rotation. Well, that was going back here, 1, 0, minus 1, 2. And then do exactly what the convolution summation says. Multiply each x and each h together, and then add up all those products. So we'll get our 1 times 1, we'll get our 2 times 2, we'll get our 3 times minus 1, our 1 times 0, totals all up, and y of n equals 0 has a value of 2. in the circular convolution result. Like the flip and shift version that we did for linear convolution, you gotta do it one index at a time and just move on to the next index. So this is y of 0. For y of n equals 1, we'll have the same h of k. So I'll put that all back up again, 1, 1, 1, 2, 3, 1 around the corner. Now we take our x of minus k, the reversed version, and I've got to rotate it by 1. In this case, we're going to rotate it counterclockwise, one position. So now it starts over here, 1, 2, minus 1, 0. And then the same game, multiply 0 times 1, 1 times 2, 2 times 3, minus 1 times 1, and get 7. Halfway home. In the convolution result, I have two sequences, each have a length of 4 that they repeat. So my circular convolution result is going to have the same number of samples. It's going to have 4 samples. You've got the first two, 0 and 1. Let's go get number 2. Same h of k. This time I need x of minus k rotated by 2 positions. So that's going to bring the 1 over here. Make our 0 or our minus 1 and our 2. Working backwards. And again, do all the products. 1 minus 1, 2 0, 3 1, 2 1, and get 4. And then, of course, the last one, y of 3. We're going to rotate the reversed x by 3. So then we take that and spin it all around to there. And that brings the 1 over here. 1, 0, minus 1, 2. Do our products. 2 times 1, minus 1 times 2. 3 times 0, 1 times 1. Add them up, and we get 1. And that's it. We can stop now. There's only 4 samples. So both our signals have a periodicity of 4. So those two, we put these two repeating patterns in the circular convolution result was, what do we get after all that? 2, 7, 4, 1. 2, 7, 4, 1. Repeats. So that gives us the one cycle of the output. Yeah.
So when we have signals or we're involving 2 signals with different periodicity, is that why we do the 0 banding?
Well, yeah. Well, sort of. See, the problem is right off the bat, they have different periodicities. I don't think my spokes and my wheels don't line up, right? So I guess I could, if I can include enough spokes so that they both have that number of periodicity, I could do it. Period of 3 and another was a period of 2, I can include 6 samples in my wheel and get a periodic result. That'd be okay. But yes, you've got to either find the least common multiple or whatever to do if they truly are periodic. Now, where the 0 pattern comes in is this little problem that we're about to encounter. So when I shut up today at 3 o'clock-ish, that will be the dividing line for time domain system analysis. That'll be the end of the first midterm. That along with the homework that you're going to turn in on Friday. Right? Where we're going next is into the world of transforms. And why are we going there? We're going there because, just like in 228, we go there because we don't like to do system analysis the way we just learned how to do it. solving difference equations for zero state response and zero input responses is a lot of work. Doing convolutions is a fair amount of work and fraught with potential for problems. So what we want to do is make that, the mathematics at least of that job, easier. And so we're going to pick up the whole problem and move it to a place where it's mathematically simpler, into a transform domain, using transforms to get in and out. And we're going to have, well, we had two kinds of transforms back in 228. Right? We had Fourier transforms and we had Laplace transforms. Fourier transforms gave us a frequency view of the world. We talked about frequency spectrum, frequency content, frequency responses of systems. And Laplace transforms, at least the one side of Laplace transforms, gave us a way to solve not just zero state responses, but total solutions, including initial conditions. We're going to do exactly all that again, except with, we're still going to have Fourier transforms, and instead of Laplace, we're going to have Z transforms. The Z transforms will do everything the Laplace transform could do for us in continuous time. Fourier, again, will do what Fourier transforms could do for us back in continuous time, except there's going to be two flavors of Fourier transform. First one we're going to talk about is called the discrete time Fourier transform. It's the correct Fourier spectrum of a discrete time signal. It's, if I took a discrete time signal and could find its Fourier transform, this is what it would look like. The bad news is it's a continuous spectrum, continuous. Meaning it's a continuous function of our digital frequency. It has values everywhere, which means when I want to combine things, I have to integrate them, which means if I want to compute them with computers, I can't do it. Computers like sums, they don't like integrals. And so some clever people said, oh, that's no good. Let's create a new thing. We'll call it the discrete Fourier transform. It'll be a discrete version of that. It'll be like a sampled version of that. It has just samples, so I can add stuff up, so I can have computers compute them, and I can deal with them that way. So this is digital stuff, right? We want computers to do things. And when we try to do convolution with this guy, we suddenly discover that our brilliant idea of sampling this to create this gave me the exact same problem that sampling things in the time domain did. Which was, in the other domain, everything got periodic. Which means if I tried to do convolutions using discrete Fourier transform math, I end up doing this kind of convolution, circular convolution, always. That's not what I want. I usually want linear convolution. And so I need a way to turn that into linear convolution when I use these guys. The answer is going to be zero padding. Add enough zeros so that circular convolution looks like linear convolution. Cheat. Trick the system. Not cheat. Intelligent adaptation of the methodology. So that's why we introduced zero padding and circular convolution. This is the convolution that's going to happen when we do it with discrete Fourier transforms. We want to do it with discrete Fourier transforms because we could do it on computers, because not only did somebody come up with a clever discrete Fourier transform, but some other guys figured out a way to do it in a very computationally efficient way that made it reasonable to do on a computer. They cut down the number of computations it takes by many orders of magnitude to compute this. And that's called the FFT, the fast Fourier transform. That's what unlocked the door to doing digital signal processing on computers, both in the time domain of difference equations and in the frequency domain of the spectrum. And so that's really the brilliance of the FFT is what made these an attractive methodology. So we need to be able to use that to do things like convolution, which means I need a way to turn circular convolution into linear. That's going to be our zero padding. We're going to see all that in the weeks to come. For now, in 30 seconds. We'll declare it the end of midterm 1, and you can study stuff for that. Homework due Friday. We're going to still move on to transforms Wednesday, so try all the problems, gives you a chance to come ask questions in office hours on tomorrow and Wednesday. Polish it up for new Friday, and on Monday. See you Wednesday.